My name is Ashley Touchton, and this is my extra credit physics video on a lecture that I went to done by Alan M. Nathan, titled The Physics of Baseball. And this is his website here that I found some extra information on in case anyone wants anything extra. So this lecture in particular sparked my interest because I know very little about baseball and I've never really thought about the physics behind it. But in particular, what in his lecture sparked my interest was the dynamics of the ball-bat collision and the idea of ball trajectories. And so moving on with that idea, I was very interested with the idea that energy is lost when the ball hits the bat. And this is due to the compression of the ball and the bat, which you don't really think about considering the ball and the bat are relatively hard objects. But when they're hit at such high speeds, they do both compress. And due to Newton's law, the bat transfers momentum to the ball. And due to Newton's law, it tells us that the ball will also transfer momentum back to the bat. And he also went on to say that 0.75 of energy is lost from the ball from the original pitch, which I thought was really interesting because that's a lot of the energy that it was originally pitched with. He also talked about the batted ball speed and how the speed that results is the result of three things. It's a result of the coefficient of restitution, the velocity of the pitch, and the velocity of the bat. And you can see from this equation here that the velocity of the bat is actually a much bigger component of that batted ball speed than the velocity of the pitch, which would not be what you would logically think at all. It's really interesting that the bat matters a lot more. So the batter plays a more critical role in that than the pitcher does. I was also really interested in this idea of the sweet spot, which he talked about. It's a specific spot on the bat where the ball needs to hit in order to get the most speed and the most distance. And if it's not hit in this specific spot, the bat is going to vibrate. And this vibration is going to take energy away from the collision and the amount of energy that will go back to the ball. I also thought it was interesting that if it's hit with enough force, the bat will actually break due to this collision if it's not hit in the sweet spot. If it's impacted outside of the nodes, the bat's going to fracture towards the pitcher. And if it's impacted, if it's impacted outside the nodes, it's going to fracture towards the pitcher. And if it's impacted inside the nodes, it's going to fracture away from the pitcher, which I thought was very interesting. So to further these sort of ideas, I was really interested in this idea of corking, because many professional players, even though it's illegal, will consider corking their bat, hollowing it out and filling it with cork. And I wondered the physics behind this. And what I found when I researched it a little bit was that the reason that batters do it is because it causes their bat to be lighter, allowing the bat to swing quicker and letting them have more accuracy. But in reality, what they don't realize is that when they hollow it out, it's actually transferring less energy to the ball because it compresses more over a longer period of time. And this longer period prevents the ball from receiving the energy back. And it also lowers the momentum of the bat because it decreases the mass, therefore lowering the momentum of the ball. So I thought that was really interesting that the physics behind this really proves that it doesn't really help anything to cork your bat. And if, as it says here, if a bat's been corked, it transfers less energy to the ball than one that had not been corked. Further, I was really interested in the ball trajectories and how I had never considered that the way a person throws a knuckleball or a spin ball or a fly ball really affects its path. And you can see this here, this spin ball, and how you can really watch its trajectory and the way it moves and the way it spins and how no one can really tell where it's going to go. So I was really interested in these different forces that affect the ball in its flight, and how the drag slows the ball, so does air resistance, and so does Magnus and gravity, which deflect the ball from its straight line. So Magnus is the effect in which a spinning ball curves away from its flight path, and it makes the ball go higher and longer, which is still minimal in comparison to air resistance. So I just thought all these forces were really interesting. And that concludes my video. Thank you very much.